We are going to present a novel single-tap latency reduction technique called PredicTaps, single-tap latency reduction with single or double-tap prediction. This work was done by Naoto Nishida from the University of Tokyo, Kaori Ikematsu, Junichi Sato, Shota Yamanaka, and Kota Tsubouchi from Yahoo Japan Corporation. Touch surfaces, such as touchpads, smartphones, and tablets, rely heavily on single and double tap inputs. And GUI apps on touch surfaces generally have components that accept both tap types. Single tap in a browser app is commonly used for selection, while double tap is used for zooming or displaying submenus. However, the conventional methods for distinguishing single and double taps have an inevitable latency problem called single tap latency. Since single-tap operations are generally the most common, this latency is a critical problem. Even such a small latency can lead to a significant time loss over a long period of time. In these methods, when the system detects a tap, it waits for a certain period of time for a subsequent tap to determine whether the detected tap was a single tap or the first tap of a double tap. If a subsequent tap occurs within that period, the system recognizes the consecutive tap as a double tap. Otherwise, it is recognized as a single tap. With this type of distinguishing implementation, a double tap event can be executed immediately after detecting the second tap, but a single tap event requires a certain time period. Most importantly, no prior works focused on this process to reduce the latency required for each tap. So, this study introduces PredicTaps, a machine learning-based method to reduce single-tap latency by predicting tap types based on sensing data. By analyzing sensing data, the system can immediately predict whether a detected tap is a single tap or the first tap of a double tap after the first tap ends. Then, the system decides whether to execute a single tap event immediately or to wait for a subsequent second tap. In this way, PredicTaps makes single and double tap events more practical without complex heuristics or detailed design. Since a user wanting to perform a double tap has to consciously decide to make 2 consecutive taps before making the first tap. This means that the double tap motion can be described as a predetermined action. A double tap is thus likely to be a faster motion than a single tap. Thus, the differences between single and double tap actions should influence the touch event-related data. In addition, we decided to use machine learning model to explore potential features. Therefore, here's our approach. First, after the first tap ends, a binary classification model predicts the system immediately predict whether a detected tap is a single tap or the first tap of a double tap, and execute a single tap event immediately if the model predicts the tap as a single. Second, PredicTaps runs on application layer so developers can on-off and optimize the model without modifying kernel programs. This is our demo. We made 2 types of game applications to let users experience the reduction of single-tap latency. The first game is Annotation Task, which users answer quizzes with 4 options with specified tap. The second game is Pointing Task, which users tap rectangles on the screens as fast as possible. And this is the difference between activated and deactivated conditions of PredicTaps. Although in Annotation Task, the ratio of latency reduction is relatively smaller than time for users to think the answer. In Pointing Task, there is a significant reduction in task completion time. In the experiment, we collected 157,996 tap data in total out of 51 participants in total. We conducted experiments under 3 conditions: laptop uncontrolled condition, smartphone uncontrolled condition, and smartphone controlled condition and user study. In the laptop uncontrolled condition, we collected the tap data from participants' daily laptop use for 5 days. In the smartphone uncontrolled condition, we collected the tap data from the game apps. This is because it was technically hard and privacy invasive to track the tap data all the time, considering that password and text inputs could be obtained from the tap locations. In the smartphone controlled condition and user study, we collected the tap data on the first day to train the PredicTaps models, and used the model to assess the usability and users' perceptions of PredicTaps. Through these experiments, we could successfully prove PredicTaps' performance, robustness, and high usability. For example, as for its performance, PredicTaps' accuracy varies from 60% to 100%. You can see this in Figure A and C in each experiment. In addition, excluding output with lower confidence made the accuracy higher, reaching 100% accuracy with 60% output with higher confidence. Besides, the total time to complete each task was significantly shortened in pointing task. This suggests that PredicTaps reduces the single tap latency. However, there is no significant difference in annotation task. We assume that this is because annotation task requires a lot of guess for users, thus the time ratio of latency does not occupy much of the total task completion time. As for the usability, NASA TLX did not show significant difference between PredicTaps on-off. This means that users did not perceive extra workload from PredicTaps. Besides, our questionnaire also suggests how users specifically perceive PredicTaps. In question 1 to 3, 14 participants perceive the latency reduction with PredicTaps. In questions 7 and 8, few people get confused the inconsistency of the latency reduction, coming from false negative cases of the prediction. In question 6, PredicTaps is regarded as useful by the participants. Besides, we also found the difference between younger people and older people in their touch features. We found that in the case of smartphone models during in the wild study and user study, models from older people scored significantly higher accuracy. We also explored to find that tapping completion time significantly differs between single and double taps among older people. This means that older people have a tendency to single tap far slower than younger people. Here we discuss PredicTaps' limitation and future possibility. As for its accuracy, we did not use much data, so in the future the models could score higher accuracy with extra or multimodal methods. Actually, we tried to use features from 9-axis sensor to develop the model by manually analyzing, but there was no improvement in the accuracy. However, in these days many deep learning models such as transformers can process the time series data in real time, so in the future these models possibly improve the PredicTaps accuracy. As for PredicTaps applicability, PredicTaps is machine learning based, so it always have the possibility of false positive. Thus, we need to take measures against that, such as apply the model only in fail-safe environments. As for the difference in controlled in the wild condition, in smartphone case, we tested the model's mean accuracy, but there is no significant difference. We assume this means that condition did not matter that much to the model's accuracy. As for training data, make use of tap data in everyday lives to fine-tune the model could improve the model accuracy. So, this is our conclusion. We developed a novel single-tap latency reduction technique, PredicTaps, which reduces single-tap latency from 150,500 milliseconds to 1,020 milliseconds by focusing on how systems can determine single or double taps. We proved these things via 2 in the wild experiments and 1 user study. First, accuracy varies from 50% with all output to 100% with 60% output with higher confidence. Second, PredicTaps is perceived as useful, as well as significantly shortening the latency in case of simple tasks. Third, tap features differ depending on ages, resulting in higher accuracy in elderly people.